The ground beneath Los Angeles has been twitching for 48 hours straight. Over 350 earthquakes. Same location, no sign of stopping. Seismologists are watching something they don't see often, a swarm that refuses to follow the rules of decay. Meanwhile, instruments across California are picking up electromagnetic signatures that some claim appeared before every major quake in modern history. And here's the kicker. The swarm is happening close enough to the San Andreas Fault to make every expert in the state refresh their monitoring stations obsessively. Stay with me until the end, because what's happening right now isn't just about one fault or one swarm. It's about whether we're watching the opening act of something California has been dreading for over a century. Subscribe and follow along, because what happens next could reveal whether this swarm is just a stress release or the opening sequence of something far bigger, and whether the electromagnetic signals, the hidden fault complexity, and the pressure building along the San Andreas for over a century and a half are finally about to converge in ways we've been dreading since 1857. This is how the big one starts in real life. Not with a headline that screams across your phone at 3 in the morning. Not with a press conference where someone in a lab coat points at a map with a laser pointer. It starts with a swarm that refuses to die. A cluster of tremors that keeps punching upward through the crust, again and again, in a rhythm that makes seismologists sit up straighter in their chairs and refresh their monitoring stations every 15 minutes instead of every hour. And right now, in the desert east of Los Angeles, near the small city of Indio and the rocky expanse around Joshua Tree, that swarm is happening. It's been happening for more than 24 hours, and it shows no sign of stopping. The numbers tell part of the story. A magnitude 4.9 earthquake struck the region as the leading event, strong enough to rattle windows and send people stumbling out of bed. That would be notable on its own, but what followed is what changed the conversation. More than 200 aftershocks in roughly 24 hours, reported publicly through seismic networks that monitor every twitch of the California crust. 200 tremors. In one day, in one concentrated area. That density alone is enough to make people nervous. But density is just one variable. The other variable is persistence. Aftershocks are supposed to decay. They're supposed to follow a pattern where the energy bleeds off, where the spacing between events grows longer, where the magnitude drops and the whole sequence fades into background noise. This swarm is not behaving that way. It surges. It quiets. Then it surges again. Seismologists have a term for this kind of behavior. They call it a sequence. The public hears 4.9 and thinks, okay, that's manageable. That's not the big one. We're fine. But seismologists watch the sequence. They watch the pattern of clustering. They watch the depth distribution. They watch the time intervals between events. Because sometimes a swarm is just a swarm, a release of stress that goes nowhere. And sometimes a swarm is a foreshock sequence, the warm-up act before a much larger rupture tears through the crust and changes the map forever. The difference between those two outcomes is the difference between a few days of nervous monitoring and a catastrophe that reshapes the infrastructure of Southern California. California lives under the permanent shadow of the big one. Everyone who lives there knows it. Everyone who visits there is reminded of it. The San Andreas Fault runs like a scar through the state, a boundary where two massive tectonic plates grind past each other in slow motion, building up stress year after year, decade after decade, until something has to give. The last time the southern segment of the San Andreas ruptured in a major way was 1857. That's more than 160 years ago. The stress has been building ever since. And the current swarm near Indio is happening close enough to the San Andreas system to set off every alarm bell in people's brains. Close enough that the question isn't just what fault is moving, but whether this movement could trigger something bigger on the main fault itself. Here's where things get strange. While the ground shakes, people are also watching the sky, not for clouds or storms, but for signals, electromagnetic signals, anomalies in the electric field, changes in the low-frequency hum of the Earth's magnetic resonance. There's a growing online conversation, fueled by independent monitoring stations and amateur researchers, claiming that the sky and the ground are showing coordinated signals at the same time. Multi-day anomalies in spectrogram data, spikes in something called the Schumann resonance quality factor, patterns that some claim have appeared before major earthquakes in the past. The scientific establishment is cautious about these claims, very cautious. But the chatter is loud, and it's spreading, and it's adding another layer of tension to an already tense situation. And then there's the cosmic coincidence. While California shakes and the internet spirals into theories about electromagnetic precursors and hidden fault triggers, something else is moving through our solar neighborhood. Something that doesn't belong here. An interstellar comet, designated 3I/Atlas, confirmed as the third known interstellar object ever detected by humanity. It didn't form in our solar system. It came from somewhere else, somewhere unimaginably distant, traveling on a hyperbolic trajectory that will carry it past the sun and back out into the void. It's faint. It's far away. It has no physical connection to the tectonic forces shaking California. But it's here. And the timing is strange enough that people are noticing. No one is saying the comet is connected to the earthquake swarm. No one credible anyway. But the fact that both are happening simultaneously, that an interstellar visitor is passing through while California experiences one of its most intense seismic sequences in recent memory, is exactly the kind of coincidence that sends the internet into overdrive. Pattern recognition is a survival instinct. We're wired to see connections, even when none exist. And when the ground under your feet won't stop moving, and someone tells you there's a visitor from beyond the solar system passing nearby, the human brain starts making links whether they make sense or not. The real question, the one that matters, is whether this swarm is an ending or a beginning. Whether the stress being released near Indio is enough to prevent something worse, or whether it's the opening act of a much larger tectonic drama. The odds of escalation are never zero. That's what breaks people. That's what keeps seismologists awake at night. Not certainty, but probability. Not knowing, but waiting. And right now, California is waiting. Next, we need to talk about the fault argument. Because here's the part nobody likes. This may not even be the San Andreas. Sometimes the scariest sentence in seismology is not that the main fault is about to break. Sometimes the scariest sentence is that it's not the main fault at all. Because when a different fault moves, a smaller fault, a fault that doesn't have a famous name or a century of research behind it, it means the system is more complicated than the simplified maps suggest. And complicated systems are unpredictable systems. That's where we are right now with the Indian swarm. Multiple reports coming out of the region suggest that the seismic activity may be concentrated along or near the Blue Cut Fault, a structure in the fault network that intersects the broader San Andreas system but operates somewhat independently. And that creates a whole new set of questions. Fault networks are not clean, single cracks running through the crust like a fracture in a pane of glass. They're more like a web of weak points, a braided system of stress concentrations where rock has failed before and will fail again. The San Andreas is the celebrity fault, the one everyone knows, the one that gets the disaster movie treatment. But surrounding it, branching off from it, running parallel to it, are dozens of smaller faults with names most people have never heard. The Blue Cut Fault is one of those. And if the current swarm is happening on or near that structure, it doesn't mean we're safe. It means we're watching stress redistribute through a network we don't fully understand. Here's the logic that keeps geologists up at night. Smaller faults can still generate damaging earthquakes. A magnitude 6 or 6.5 event on a secondary fault can collapse buildings, rupture pipelines, and kill people. But smaller faults can also do something else. They can act as stress transfer points. When one fault moves, it changes the stress field around it. It pushes pressure onto nearby structures. Sometimes that pressure dissipates harmlessly. Sometimes it finds a pathway to a much larger fault and triggers a rupture that wouldn't have happened otherwise. The analogy people use is a pressure cooker. You hear tiny clicks as the metal expands, then silence, then one hard pop as the seal gives way. That's what fault interaction looks like in slow motion. The Indian swarm has a personality. It's not a smooth, predictable decay curve. It clusters. It surges. It goes quiet for a few hours, just long enough for people to relax, and then it surges again. That uneven behavior is what makes seismologists nervous. Aftershocks from a single main shock event typically follow a well-studied pattern called Omori's Law, where the rate of aftershocks decreases over time in a predictable way. Swarms don't always follow that pattern. Swarms can have multiple peaks. Swarms can migrate along a fault, and in rare cases, swarms can include foreshocks, meaning the largest earthquake hasn't happened yet. The public discourse right now is emphasizing preparedness regardless of which fault is involved. That's the responsible message. Check your emergency kit. Know your evacuation routes. Have a plan. But underneath that practical advice is a deeper, more uncomfortable truth. The odds of escalation are low, but they are not zero. And that non-zero probability is what keeps the fear alive. Because no one can tell you with certainty that the swarm will stop. No one can promise that the magnitude 4.9 was the peak. All they can do is watch the data and update the probabilities as new events occur. What makes this moment even more surreal is the context. The swarm is not happening in isolation. There's been increased seismic activity offshore near Oregon, significant enough to catch attention. There's ongoing conversation in the seismology community about stress transfer along the Cascadia subduction zone and the broader Pacific margin. And there's the persistent hum of electromagnetic anomaly reports, the claims that instruments are detecting precursor signals in the days leading up to major seismic events. None of this is confirmed. None of this is part of the official forecast. But it's all part of the atmosphere. The sense that the West Coast is experiencing a period of elevated tectonic restlessness. And then there's the visitor. 3I/Atlas, the interstellar comet, continues its silent trajectory through the solar system, indifferent to the tectonic forces reshaping California. It's a reminder that the universe operates on scales and timelines that dwarf human concerns. A comet that traveled for millions of years through the void doesn't care about fault lines or earthquake swarms, but its presence adds a layer of cosmic strangeness to the moment. A sense that multiple systems, both terrestrial and extraterrestrial, are converging in ways we don't fully understand. Imagine standing in the desert near Joshua Tree, feeling the ground twitch beneath your feet every few hours, watching the stars at night, knowing that one of those faint points of light is not a star, but a visitor from another solar system. It's the kind of moment that makes you realize how fragile our sense of stability really is. We think of the Earth as solid, reliable, unchanging, but it's not. It's a dynamic, restless planet, constantly reshaping itself through forces we can measure, but not control. And right now, one of those forces is playing out in real time beneath Southern California. The fault argument matters because it determines how we interpret the swarm. If it's happening on the San Andreas, the implications are one thing. If it's happening on a nearby secondary fault, the implications are different, but not necessarily less concerning. Either way, the pressure is moving, the crust is adjusting, and the only certainty is that we're watching a system in motion, trying to predict its next move based on incomplete data and imperfect models. Now, We go where scientists argue and the internet goes feral. We're diving into electromagnetic anomalies, precursor signals, and the question that refuses to die. Can we predict earthquakes by watching the sky? Some people aren't watching the ground. They're watching the air. They're monitoring electric field spectrograms, tracking ultra-low frequency oscillations, and comparing real-time data to historical baselines from previous major earthquakes. And according to some of these monitors, something unusual has been happening in the days leading up to the Indio swarm. Multi-day electromagnetic anomalies. Spikes in the quality factor of the Schumann resonance. Patterns that, if you believe the claims, match the signatures detected before other significant seismic events. The problem is that none of this is confirmed by mainstream seismology. None of it is part of the official earthquake forecasting toolkit. And yet, the conversation refuses to go away. The Schumann resonance is real. It's not a fringe concept or pseudoscience. It's a well-documented phenomenon where the space between the Earth's surface and the ionosphere acts as a waveguide for extremely low-frequency electromagnetic waves, primarily generated by lightning strikes around the globe. The Earth hums like a bell, resonating at a fundamental frequency of about 7.83 Hz, with several higher harmonics. That hum is constant, measurable, and has been studied for decades. What's controversial is whether changes in that hum, specifically changes in the sharpness or quality factor of the resonance peaks, can serve as a precursor to earthquakes. The split-screen debate goes like this. On one side, you have researchers and independent monitors who argue that they've observed correlations between electromagnetic anomalies and subsequent seismic events. They point to case studies, to time series data, to statistical analyses showing that certain types of EM activity appear more frequently in the days before major quakes. They argue that the piezoelectric effect, where stressed crystalline rock generates electric fields, could explain the connection. That as tectonic stress builds, the rock literally produces electromagnetic signals that propagate through the crust and into the atmosphere. On the other side, you have the institutional skeptics who argue that correlation is not causation, that EM anomalies happen all the time, for all kinds of reasons, from solar activity to atmospheric disturbances to equipment malfunction. That cherry-picking events where an anomaly preceded an earthquake ignores all the times anomalies occurred and nothing happened, or earthquakes occurred with no preceding anomaly. Here's a useful framework. Think of it as the two-lens model. The instrument lens shows you what the sensor actually measures. A spike in electric field intensity, a change in spectral power distribution, a shift in resonance quality. Those measurements are objective. They're either there or they're not. But then there's the interpretation lens, the story humans build from the data. And that's where things get messy. Because the same dataset can support multiple narratives depending on what you choose to emphasize, what you choose to ignore, and what prior assumptions you bring to the analysis. This topic explodes online because it feels like cheat codes for nature. It gives people the illusion of control, the sense that if we could just crack the electromagnetic signature, we could predict earthquakes hours or days in advance and save thousands of lives. It's seductive. And it's been seductive for decades. Electromagnetic precursors have been claimed before nearly every major earthquake, from Loma Prieta in 1989 to Fukushima in 2011. But the reliability has been disputed every single time. No consensus method exists today that turns EM spikes into a quake forecast you can bet your life on. That's the brutal truth. The instruments pick up signals. The interpretation remains contested. So when people report multi-day anomalies in the electric field spectrogram leading up to the Indio swarm, what does that actually mean? It means the instruments detected something. Whether that something is causally related to the seismic activity, or whether it's an unrelated atmospheric phenomenon that happened to occur at the same time, is a question that requires far more data, far more controls, and far more validation than currently exists. The scientific process demands rigor. The internet demands answers, and that mismatch creates fertile ground for speculation. And then you add the cosmic fuel. When a rare interstellar comet shows up during the same window as an intense earthquake swarm, people start looking for meaning everywhere. 3. I/Atlas is a confirmed visitor, the third known interstellar object detected by humanity. It was discovered by the Atlas Survey System, the Asteroid Terrestrial Impact Last Alert System, which scans the sky for near-Earth objects and other transient phenomena. The comet's trajectory is hyperbolic, meaning it came from interstellar space and will return to interstellar space. It didn't form in our solar system. It's passing through, a brief guest on a journey measured in millions of years. There is no physical mechanism by which an interstellar comet, millions of kilometers away, could influence tectonic activity on Earth. Gravitational effects are negligible. Electromagnetic effects are non-existent at that distance. But that doesn't stop the speculation. What if transient electromagnetic conditions in the solar environment, combined with stressed fault systems on Earth, create coincidences that look like correlations? What if the same cosmic timing that brings a visitor from deep space also coincides with periods of elevated seismic activity? Not because one causes the other, but because both are part of larger, interconnected cycles we don't yet understand. It's a seductive narrative. It's also almost certainly wrong, but the human brain loves patterns, especially when the stakes are high and the uncertainty is overwhelming. Here's what we know for sure. The Indian swarm is real. The electromagnetic anomaly reports are real in the sense that instruments detected something. 3I/Atlas is real, confirmed as an interstellar comet by multiple observatories. What we don't know is whether any of these things are connected in a meaningful way. And that uncertainty is exactly what keeps the conversation alive. Because if there's even a 1% chance that electromagnetic monitoring could provide early warning for a major earthquake, the potential payoff is enormous. But chasing that 1% has consumed careers, funding, and credibility for decades, and we're still not there. The atmospheric tension right now isn't just about the Indian swarm. It's about the convergence of signals, real and imagined, that make this moment feel different. The persistence of the seismic sequence, the electromagnetic chatter, the interstellar visitor, the broader context of increased activity along the Pacific margin. None of it proves anything. All of it feeds the narrative that something bigger might be coming. If you think this is just Indio, just one localized swarm in the Southern California desert, zoom out. Because the story being written right now isn't about one fault in one location. It's about a coastline under pressure, a network of faults responding to stress in ways we're only beginning to map. And that's where things get really interesting. This is where people stop thinking earthquake and start thinking sequence, where the mind shifts from a single event to a chain reaction, from an isolated rupture to a cascading series of adjustments that ripple through the crust like shockwaves through water. The West Coast pressure transfer narrative has been building for years, fueled by research into fault interactions, stress modeling, and the uncomfortable realization that the Pacific margin is not a collection of independent fault systems, but a single, interconnected mechanical structure. And right now, with the Indio swarm intensifying and reports of increased offshore activity near Oregon, that narrative is gaining traction in online forecasting communities and alternative seismology circles. The offshore activity matters. More movement offshore, particularly along the Cascadia subduction zone or related structures, has people watching the margin with renewed intensity. The Cascadia zone is a different beast than the San Andreas. It's a subduction zone where the oceanic Juan de Fuca plate is sliding beneath the North American plate, building up stress for a potential megathrust earthquake that could dwarf anything the San Andreas is capable of producing. The last time Cascadia ruptured in a major way was January 26, 1700, a magnitude 9 event that sent a tsunami across the Pacific to Japan. That was more than 300 years ago. The recurrence interval for Cascadia megaquakes is somewhere between 200 and 800 years. We're inside the window, and any significant offshore activity naturally raises the question of whether the subduction zone is adjusting in ways that could influence the broader stress field along the coast. Pressure transfer is a real phenomenon. It's not fringe science. When one fault moves, it changes the stress distribution on nearby faults. Think of it like stepping on a cracked sidewalk tile. The weight shifts. The pressure redistributes. Sometimes the tile next to it cracks. Sometimes the stress dissipates harmlessly. Seismologists use sophisticated models to calculate how stress transfers through fault networks, looking for patterns that might indicate increased hazard on certain segments after a triggering event elsewhere. But here's the catch. The models are probabilistic. They can tell you that stress increased on a particular fault after an earthquake, but they can't tell you when or if that fault will actually rupture. Timing is the unresolved variable. The alternative forecasting ecosystem operates in a different space than institutional seismology. It uses watch windows, corridor targeting, and pattern recognition based on historical sequences rather than physics-based stress models. Some of these forecasters have identified a corridor stretching from Los Angeles to the Salton Sea as a zone of elevated concern, arguing that the current swarm fits a pattern observed before previous significant events. Others talk about global transfer, the idea that stress changes in one part of the planetary crust can influence seismic activity in distant regions through mechanisms that aren't fully understood. These concepts exist on the edge of credibility. Some are grounded in legitimate observations. Others are wishful pattern matching. The challenge is sorting signal from noise. Why do these narratives spread? Because they offer pattern recognition during uncertainty. They turn randomness into storyline. They give people a framework for understanding events that otherwise feel chaotic and uncontrollable. When the ground won't stop shaking, and the official message is we're monitoring the situation but can't make specific predictions, the human brain craves something more concrete. Alternative forecasters provide that. They offer dates, locations, magnitude estimates. Sometimes they're right. More often, they're wrong. But the hits are remembered, and the misses are forgotten, and the cycle continues. Scientists do study stress interactions. They absolutely model how one fault rupture can increase or decrease stress on nearby faults. But predicting exact timing and location remains unresolved. The gap between understanding that stress transfer exists and being able to forecast when and where the next rupture will occur is enormous. It's the difference between knowing that a dam under pressure will eventually fail and being able to predict the exact second the concrete cracks. Seismology is very good at the former. It's still struggling with the latter. And then you layer in the cosmic element. 3 I/Atlas, the interstellar comet, continues its trajectory through the inner solar system, a faint smudge of light visible only to powerful telescopes. It's a scientific curiosity, not a Hollywood sky object. You can't see it with the naked eye. It's not trailing a brilliant tail across the heavens, but it's there, confirmed and tracked. A visitor from a place so distant that the light from the nearest stars hasn't had time to reach us since the comet began its journey. And the fact that it's passing through during this particular window of tectonic restlessness along the West Coast is exactly the kind of coincidence that fuels myth-making. People want connections. They want causality. They want the universe to make sense. When an interstellar visitor appears at the same time the ground is shaking, the brain looks for links, even when none exist. Maybe it's solar activity affecting both electromagnetic conditions on Earth and the visibility of the comet. Maybe it's pure chance. Maybe it's confirmation bias. where we notice the coincidences and ignore the countless times comets pass without corresponding seismic events. But the narrative persists because it satisfies a deep psychological need for meaning in chaos. Here's the brutal truth. Even if the alternative forecasters are wrong about timing, about specific corridors, about global transfer mechanisms, the fact that the current sequence fits the pattern they've been describing is what makes it dangerous. Because it means enough people are paying attention, enough people are prepared to interpret any escalation as validation of the forecast, that the social response to a major earthquake could be shaped by narratives that have nothing to do with the actual geophysics. And that creates its own kind of instability. The West Coast is not one's fault. It's an interconnected machine, a network of structures responding to the relentless grinding of tectonic plates. The Indian swarm is one data point in that larger system. The offshore activity near Oregon is another. The electromagnetic anomaly reports are another. And somewhere in the mix is an interstellar comet, a reminder that the universe is vast, indifferent, and full of visitors we never expected. None of it proves a catastrophic rupture is imminent. All of it contributes to the sense that something is shifting, that the quiet period might be ending, that the big one could be closer than we'd like to believe. Now here's the twist nobody's ready for. The fault map might be missing pieces. Big pieces. Hidden structures beneath Northern California that we only discovered because tiny earthquakes started drawing them for us. The scariest disasters don't come from what we don't know. They come from what we think we know. From the confident assumptions that turn out to be wrong. From the simplified models that miss critical details. From the maps that show clean lines when the reality beneath our feet is far more complex. And right now, new research from Northern California is rewriting our understanding of the fault systems that run through the state, revealing hidden structures that were invisible until tiny earthquakes started lighting them up like tracer rounds in the dark. The research involves microseismicity, the constant background tremor of small earthquakes that most people never feel, but seismic networks record constantly. These tiny earthquakes, often magnitude 2 or smaller, act like X-rays for the crust. Each event is a point of failure, a place where stress exceeded the strength of rock and caused a small slip. When you plot thousands of these events over time, patterns emerge, alignments, clusters, linear trends that outline structures you can't see from the surface. And in Northern California, those patterns have revealed something unexpected. A tectonic fragment, a hidden piece of the crust, possibly a remnant of ancient plate interactions, sitting beneath the region in a configuration that doesn't match the simplified fault maps most people reference. The key concept here is that tiny earthquakes matter. They're not just noise, they're diagnostic tools. Every microseismic event represents a failure point in the crust, and when you aggregate enough of them, they outline the geometry of hidden faults and structural boundaries. It's similar to how astronomers use occultations to map the shapes of distant objects. You can't see the object directly, but you can see the shadows it casts, the way it blocks light, or in this case, generates seismic energy. The crust is opaque. We can't drill down far enough to see the structures directly, but the earthquakes themselves illuminate the architecture. What does this mean for the Indian swarm? It's not a direct connection. Northern California is hundreds of miles from the current seismic activity near Joshua Tree, but the discovery proves something important. It proves that the fault system beneath California is more complex than the simplified public maps suggest. It proves that structures we didn't know existed can influence stress distribution in ways we haven't modeled. And it raises the uncomfortable question of what else we're missing. If a tectonic fragment can hide beneath Northern California until microseismicity reveals it, what other hidden structures exist beneath Southern California? What other pathways for stress transfer are we not accounting for? California isn't one's fault. It's an interconnected machine, a three-dimensional network of structures that extends deep into the crust and mantle. The San Andreas gets the attention because it's long, it's active, and it runs through densely populated areas. But surrounding it, intersecting it, branching off from it, are countless other faults. Some are mapped, many are not. Some are active, some are dormant, but could reactivate under the right stress conditions. And the more we learn about the subsurface architecture, the more we realize how incomplete our models really are. This is where the big one fear gets complicated. The public imagines a cinematic rupture, a single massive earthquake that tears through California from end to end, collapsing bridges and toppling skyscrapers in a disaster movie climax. That could happen. The southern San Andreas is certainly capable of producing a magnitude 7.8 or larger event, but reality could also be messier. Multi-fault cascades, where one rupture triggers another on a nearby structure, creating a sequence of damaging earthquakes spread over hours or days. Unexpected segments lighting up on faults we didn't think were capable of major ruptures. Hidden structures failing in ways that bypass our hazard models entirely. The controversy angle here is subtle, but important. Official hazard models evolve as new data becomes available. That's how science works. Models improved, probabilities get updated, maps get redrawn. But the public expects certainty. They want to know which faults are dangerous and which aren't, which areas are safe and which should be evacuated. Science offers probability and revisions. There's a 30% chance of a magnitude 7 or larger earthquake in Southern California in the next 30 years. That number might go up or down as new research comes in. That's not evasion. That's honesty. But it's frustrating for people who want definitive answers. And then there's the cosmic lens. We spot an interstellar object like 3I/Atlas because it moves oddly, because its trajectory doesn't match the elliptical orbits of solar system natives. We spot hidden faults because microseismicity moves oddly, because the pattern of tiny earthquakes doesn't match what we'd expect from known structures. In both cases, anomalies are real reality. The universe doesn't advertise its secrets. It forces us to notice when things don't fit the expected pattern. 3I/Atlas is confirmed as interstellar comet number 3, a visitor from the void that announced itself through its strange path across the sky. The hidden tectonic fragment beneath Northern California announced itself through the strange clustering of microseismic events that didn't align with known faults. The machine beneath California is bigger and stranger than the maps on the wall at the local emergency management office. Every new dataset reveals more complexity. Every improvement in monitoring resolution shows structures we missed before. And the Indio swarm, whatever it turns out to be, is happening within that complex machine. Not on a single, well-understood fault, but within a network of interacting structures where stress can transfer in unexpected ways, where hidden pathways can channel energy toward ruptures we didn't see coming. If Earth can surprise you with hidden faults and tectonic fragments that stayed invisible for decades, space absolutely can surprise you too. And we're about to launch humans into it, back toward the moon, using hardware that's been sitting in storage for years, waiting for this exact moment. While California listens for cracks in the crust, while seismologists refresh their monitoring stations and alternative forecasters update their watch windows, NASA is lighting the fuse on the next era of human spaceflight. The hardware is rolling. The timeline is tightening. And in a development that's easy to miss if you're focused on earthquake swarms and interstellar comets, the Artemis II mission stack has moved toward Launch Pad 39B at Kennedy Space Center. The Space Launch System rocket and the Orion crew capsule, together forming the most powerful launch vehicle NASA has built since the Saturn V, are now in position for a crewed lunar flyby mission that will send humans beyond low Earth orbit for the first time since Apollo 17 in 1972. Artemis Seku is not a landing mission. It's a systems test. 4 astronauts will launch atop the SLS, enter a trajectory that swings them around the far side of the moon, and return to Earth. The mission is designed to validate life support systems, test deep space communications, and prove that Orion can keep humans alive beyond the protective cocoon of Earth's magnetosphere. It's the necessary step before Artemis III attempts an actual lunar landing. And the fact that it's happening now, in 2025, means that decades of planning, billions of dollars in development, and countless engineering challenges are converging toward a launch window that will either validate the program or expose critical flaws. The contrast is striking. We engineer rockets for brutal conditions. We design thermal protection systems that can withstand re-entry temperatures hot enough to vaporize steel. We build guidance computers that can navigate to the moon with insane precision, correcting trajectory errors measured in meters per second across distances of hundreds of thousands of kilometers. Yet cities remain vulnerable to basic ground shaking. Buildings collapse, bridges fail, pipelines rupture, not because we don't understand the forces involved, but because retrofitting infrastructure is expensive, politically complicated, and easy to defer until after the disaster happens. There's a parallel here with 3I/Atlas that's worth drawing out. The interstellar comet is a visitor from deep time, an object that formed in another solar system billions of years ago, and has been traveling through the galaxy ever since. It represents a connection to the distant past, to the epoch of planetary formation, to processes that shaped the universe long before Earth existed. Artemis represents the opposite. It's humanity trying to leave the cradle, trying to become a species that doesn't rely on a single planet for survival. One is a reminder of where we came from. The other is a statement of where we're trying to go. But both involve navigation through hostile environments using incomplete information. We can track 3I/Atlas with telescopes, measure its trajectory, calculate its orbit. But we don't know exactly what it's made of, how stable its structure is, or what it looked like before it entered the inner solar system and started sublimating under solar heating. Similarly, we can plan Artemis missions with extraordinary precision, model every phase of flight, simulate every failure mode. But we can't eliminate uncertainty. Hardware fails. Unexpected interactions occur. And when you're operating hundreds of thousands of kilometers from Earth, with minutes of communication delay and no possibility of immediate rescue, that uncertainty becomes existential. What makes this moment surreal is the collision of timescales. Earthquakes operate on geological time. The stress building on the southern San Andreas has been accumulating for more than 160 years. That's multiple human lifetimes, but it's a blink in geological terms. 3I/Atlas has been traveling for millions of years. Its journey from its home solar system to ours spans timescales that make human history irrelevant. And Artemis operates on engineering timescales, measured in test cycles and launch windows and mission durations counted in days. All three are happening simultaneously, intersecting in this particular moment in January 2025. There's something mind-blowing about the asymmetry. We've mastered propulsion. We can light-controlled chemical explosions, powerful enough to lift hundreds of tons of hardware to orbital velocity and beyond. We can rendezvous spacecraft in orbit with centimeter-level precision. We can land rovers on Mars using supersonic parachutes and rocket-powered sky cranes. But we can't schedule the ground under our feet. We can't tell California when the next major earthquake will occur, where it will rupture, or how much damage it will cause. Prediction, at least earthquake prediction, remains stubbornly out of reach despite decades of research and monitoring. The Artemis timeline is real. It involves actual deadlines, actual launch windows dictated by orbital mechanics and lunar positioning. Missing a launch window means waiting weeks or months for the next opportunity, with all the cost and schedule implications that entails. The mission has already been delayed multiple times. Hardware issues, software updates, safety reviews. But it's moving forward now, inching closer to the moment when 4 humans strap themselves to the top of a controlled explosion and trust that every system will work as designed. And somewhere in the background, barely visible even to powerful telescopes, 3I/Atlas continues its ancient journey. It doesn't care about launch schedules or earthquake swarms. It's governed by gravity and momentum, following a trajectory determined by forces that acted billions of years ago in a solar system we'll never see. Its presence is a reminder that the universe is full of visitors, that the solar system is not a closed loop, but a dynamic environment where objects enter and exit constantly, most of them too small or too distant to notice. The closing thought here is simple but profound. We've mastered propulsion. We've mastered navigation through space. We've even mastered survival in one of the most hostile environments humans have ever attempted to operate in. But we haven't mastered prediction. We can't control earthquakes. We can't schedule tectonic events. And as Artemis rolls toward the launch pad and California continues to shake, that gap between what we can engineer and what we can forecast becomes painfully obvious. And the last piece is where science starts to feel like magic, where artificial intelligence begins designing matter backwards, starting with the desired outcome and working back to the molecular structure that will produce it. It's already happening, and it's changing the rules of materials science faster than most people realize. We can't control earthquakes. We can't predict them with the precision needed to save lives at scale. We can't schedule tectonic ruptures or prevent faults from accumulating stress over decades and centuries. But we're learning to control outcomes in other parts of physics. We're learning to design materials with specific properties by working backwards from the desired result, using artificial intelligence to navigate possibility space in ways that would take human researchers lifetimes to explore manually. And that shift, that transition from discovery to design, is one of the most profound changes happening in science right now. It represents a fundamental inversion of how we approach problems, moving from the question of what can we do with what we have to the question of what do we need and how do we create it. The AI discovery race is real. Machine learning algorithms are being trained on massive datasets of molecular structures, material properties, and experimental outcomes. The AI doesn't understand chemistry the way a human chemist does. It doesn't have intuition or creativity in the traditional sense. It can't walk into a lab and smell when a reaction is going wrong or feel the texture of a novel polymer, but it can pattern match at scales that are impossible for humans. It can identify correlations between molecular configurations and macroscopic properties that would never occur to a researcher working from first principles. And increasingly, it can propose new materials, new molecular structures that have never been synthesized before, but which the AI predicts will have desirable properties. The algorithms are exploring chemical space, that vast multidimensional landscape of possible molecular arrangements, with a speed and thoroughness that makes traditional methods look glacial by comparison. This is backwards design. Instead of starting with available materials and figuring out what you can build with them, you start with the performance you need and ask the AI to generate a molecular structure that will deliver it. Need a battery material with higher energy density and longer cycle life? Describe the target properties, feed them into the model, and let the AI search chemical space for candidates. Need a structural material that's lighter than aluminum but stronger than steel? Same process. Define the constraints, let the algorithm explore millions of possibilities, and synthesize the top candidates to see if they work in practice. The AI becomes a kind of molecular architect, designing structures optimized for specific functions before they even exist in physical form. The speed is what's revolutionary. Traditional materials discovery involves intuition, trial and error, serendipity, and years of incremental refinement. A researcher might spend an entire career exploring variations on a single class of compounds, testing compositions, tweaking synthesis conditions, and slowly building understanding through accumulated experience. AI-assisted discovery compresses that timeline, not from years to months, but from years to weeks, or even days in some cases. The algorithms don't replace human expertise. They amplify it. They handle the combinatorial explosion of possibilities that makes exhaustive search impractical, narrowing the field to promising candidates that human researchers can then validate experimentally. It's collaboration between silicon and carbon-based intelligence, each contributing what it does best. The implications extend far beyond material science. Drug discovery is being transformed by similar approaches, with AI systems proposing molecular structures for pharmaceuticals based on desired biological activity. Catalyst design, semiconductor engineering, polymer chemistry, all are being reshaped by machine learning methods that can navigate complexity at superhuman speed. We're entering an era where the bottleneck shifts from ideation to validation, from thinking of what to try to actually making it and testing whether it works. That's a profound shift in the pace of technological development. But here's the contrast that makes this relevant to the earthquake conversation. Civilization invests heavily in frontier technology. We pour billions into space exploration, artificial intelligence, quantum computing, advanced materials. We chase the bleeding edge of what's possible, pushing the boundaries of human capability in domains that feel futuristic and transformative. These are the projects that capture imagination, that attract funding, that make headlines. But we neglect boring resilience. We defer earthquake retrofits because they're expensive and the buildings haven't fallen yet. We underfund seismic monitoring networks because adding more sensors doesn't produce dramatic breakthroughs, just incremental improvements in data quality. We allow critical infrastructure to age past its design lifetime because replacement is expensive and politically unglamorous. Bridges built in the 1950s are still carrying traffic loads they were never designed for. Water systems installed decades ago are corroding beneath cities. Power grids operate on equipment that predates modern computing. The gap between what we're capable of building and what we're willing to maintain is enormous and growing. There's a psychological asymmetry at work. Innovation feels like progress. Maintenance feels like treading water. Building something new creates ribbon-cutting ceremonies and career advancement. Keeping something old functional creates neither headlines nor promotions. So we build cities on fault lines and convince ourselves that the next big one won't happen on our watch. We design buildings to code, which means they're engineered to survive an earthquake without collapsing, not necessarily without being damaged beyond repair. That's an economic calculation disguised as an engineering standard. The goal is life safety, not continued function. And in the aftermath of a major rupture, when hospitals are damaged, when bridges are impassable, when water mains have burst and power is out, that distinction matters enormously. Earthquakes are proof that the planet sends random reminders. Ruptures that release stress accumulated over decades or centuries, that reshape the landscape in seconds, that we can monitor but not prevent. They're expressions of systems far larger and older than human civilization, operating on timelines that make our planning horizons look absurdly short. The stress building on the southern San Andreas right now has been accumulating since 1857. That's 168 years, multiple human lifetimes, long enough that no one alive today has personal memory of the last major rupture on that segment. And that temporal distance makes it easy to treat the threat as abstract, as something that might happen someday, rather than something that will happen eventually. And yet we persist in thinking we can engineer our way to safety. We design rockets that can navigate to the moon with centimeter-level precision. We train AI systems that can discover new materials by exploring billions of molecular configurations. We map the human genome, split atoms, detect gravitational waves from colliding black holes billions of light years away. But We can't predict when the ground will shake. We can't schedule tectonic events. And that asymmetry, that gap between what we can control and what we can't, is one of the defining tensions of technological civilization. It's not stupidity. It's optimism bias, the psychological tendency to believe that bad outcomes happen to other people, in other places, at other times. The odds of a major earthquake in Southern California in the next 30 years are significant, somewhere between 20 and 30% depending on which model you trust. But 30 years is long enough that it's easy to defer action, to assume that future generations will handle it, to focus on immediate concerns instead of low probability, high consequence events. Politicians operate on election cycles. Infrastructure projects operate on budget cycles, and both are measured in years, not decades. The mismatch between geological timescales and human institutional timescales creates a systematic bias toward underinvestment in resilience. The narrative fuel right now, the thing that's driving the online conversation about the Indio swarm and electromagnetic anomalies, is that multiple concerning signals are appearing simultaneously. The swarm itself is not unprecedented, but its persistence and intensity are notable. The electromagnetic anomaly reports, whether validated or not, are part of a decades-long conversation about earthquake precursors that refuses to die despite mainstream scientific skepticism. And the broader context of increased seismic activity along the West Coast, from offshore Oregon to Southern California, creates a sense that the entire margin is experiencing elevated stress. Whether these signals are causally connected or merely coincidental is the question that divides believers from skeptics. So here are the three layered conclusions. First, the Indio swarm is confirmed, real, and intense. More than 350 earthquakes in 48 hours, centered near a region where multiple fault systems intersect, with no clear indication that the sequence is over. Seismologists are monitoring continuously. The public is nervous, and the odds of escalation, while low, are not zero. That non-zero probability is what keeps people awake at night, refreshing earthquake monitoring websites, feeling every creak in their house as potentially significant. Second, electromagnetic anomalies may or may not mean anything predictive. The instruments detected something. Whether that something is causally related to the seismic activity or whether it's coincidental atmospheric noise remains unresolved. There is no scientific consensus that EM monitoring can reliably forecast earthquakes with the specificity needed for public warnings. But the conversation persists because the potential payoff is too large to ignore. If electromagnetic precursors are real, if they can provide even hours of advance warning, the lives that could be saved justify continued research. But until the signal-to-noise problem is solved, until false positives are eliminated and reliability is proven, these methods remain on the margins of seismology, rather than at its core. Third, the timing feels significant, even if the connections are unclear. A major swarm near the San Andreas, electromagnetic anomalies reported by independent monitors, increased offshore activity, hidden fault complexity being revealed by new research, all happening in the same narrow window. That convergence drives speculation, pattern recognition, narrative construction. Humans are storytelling creatures. We see plots where probability sees randomness. And when multiple rare events occur close together in time, the brain insists on finding meaning even when none may exist. If the big one doesn't happen this week, that doesn't mean the warning was fake. It means we're living inside probabilities. It means the stress is still accumulating, the fault systems are still interacting, and the machine beneath California is still running. Every earthquake is a data point. Every swarm is an opportunity to refine models and test hypotheses. And every moment of heightened attention, even if it doesn't result in a catastrophic rupture, is a reminder that resilience isn't built during disasters. It's built in the quiet periods, when nothing is happening, when it's easy to assume that nothing will. Next episode, I'm going to show you what changed in the data after the swarm, because that's where the real story hides. In the stress transfer patterns, the aftershock decay rates, the subtle shifts in seismic velocity that indicate how the crust responded to the sequence. The headlines move on, the scientists keep watching, and the machine keeps running, indifferent to whether we're paying attention or not.